Okay, moving on to the next section. This is graphing linear inequalities in two variables. So previously, we've been doing linear equalities. Now we're doing inequalities in this section. So what do graphs of inequalities in two variables look like? So a linear equality in one variable can be written in this form. Linear inequalities in one variable are written in these following forms. All right, so notice that we've got all of these inequalities here. Okay, but what we're doing is we are treading over past material where we're talking about one variable. This is what we did in the past, but we're concerned with two variables now. So solutions in a linear inequality in one variable is a value of x which results in a true inequality equation. So when it comes to linear inequalities in two variables, it's written in this form. I'm sorry, that's a linear equality. It has an equal sign there. A linear inequality in two variables can be written in any of these four forms. So you can see how it looks similar to what we did with one variable, but now we've got two. We've got x and y with an inequality sign. Okay. So solutions to inequalities in two variables are two values of x and y, which results in a true inequality equation. So moving on to the next page, I took the liberty of kind of doing some of the math here, and I'll kind of explain what I did in order to save time. So let's look at solutions to linear inequalities in two variables. So let's determine if the following ordered pairs are solutions to the inequality in two variables. So here we've got our inequality. Y is greater than or equal to x plus 4. And we're going to put each of these points in. So part A here is to put the point 0, 0 into that inequality. So when we substitute 0 in for y and 0 in for x, we end up with this false inequality. It's false because 0 is not greater than 4. Okay, so that's false. And we put in another ordered pair of x and y. So we'll put in the point -2, +2. So we put 2 in for y, we put -2 in for x, and we simplify this, and we get 2 is greater than or equal to 2. That is a true statement. So this point, 2, 2, I'm sorry, -2, +2, this is our first true solution to this inequality. Okay, this is our first solution to that inequality because it rendered a true statement. This next point that I looked at is the point -5, -9. So put negative in 9 for y, put -5 in for x, and simplify. And -9 is not greater than -1, right? So that's false. And then we've got -5, +4. So put 4 in for y, -5 in for x, and simplify. And that's a true statement. So -5, +4 is also a solution. Okay, we try the point 4, -4. So put -4 in for y, +4 in for x, and this generates a false statement. Okay, now looking at 5 more points, we have a point 1,5. Okay, that generates a true statement. So 1,5 is a solution. Put in the point 510. That renders a true statement. So 510 is also a solution. We can put -7, -1 in. And that also generates a true statement. So this is a solution. And the point 36, put 6 in for y, 3 in for x, simplify, and 6 is not greater than 7. So that's a false statement. In this last one, J, put in -5 in for y, -8 in for x, and simplify. we see that -5 is not greater than -4. So that's a false statement. So we've put, all of these points into our inequality here, and some were solutions and some were not. So the next thing I want to do is I want to take all of those points and plot them. And so the ones that were solutions that gave a true statement, I've plotted in green. And the ones that were false, that were not solutions, I plotted in red. Now, it might have been a little more helpful to do a few more points, but I think this is maybe just enough to get an idea of what's going on. So are you starting to see a pattern as far as where the solutions are and where the solutions are not? So again, green closed dots are solutions, and red open dots are not solutions. So you can kind of see that it appears as though the solutions are kind of like on this side of the graph, something like that maybe. Okay, this appears to be where all of our solutions are. And everything that's kind of down and to the right, that is kind of what appears to be where our solutions are not. Well, let me add another line in here. So remember, our inequality is y greater than or equal to x plus 4. But let me graph the line y equals x plus 4. Let me graph this. So if I graph this, it's got a y-intercept of 4, and then we've got a slope of 1. So that's going to be this line right here. All right, so this is y equals x plus 4. So what do you notice about this line? It appears any point that is on this line, any point that is, okay, any point that is on the line or above it is a solution. So any point that we choose in this green shaded area that I've made here will be a solution to that inequality. So solutions for a linear equality are on a line like this. Solutions for an inequality is going to be in an area. So that's where solutions are kept. That's where they're found for inequalities. So here, I said, is there a pattern to closed and open points? Okay, now graph this as an equality, which is what I did. So this equality is, this equation here is kind of our boundary between solutions and not solutions. And when you kind of look at this inequality, it says y is greater than or equal to x. So when you see this greater than, you kind of think, well, greater values of y are up here. All right, so that kind of gives a hint as to where those solutions can be found. All right, so notice that we've got greater than or equal to, and with greater than or equal to, points on the line are also solutions, right? This point was on the line, that was a solution, and this point was on the line, and that was a solution. So this next part is asking, how would the example change if instead of an equality with equals, like greater than or equals to, we just had greater than. And so the answer to this is that values above y equals x plus 4 would be true, but values on y equals x plus 4 would be false. So the previous page, we graphed y greater than or equal to x plus 4. Now we're going to graph y equals, or I'm sorry, y is greater than x plus 4. So we're going to graph the same line, the y-intercept of 4, but now we're going to put a dashed line, not a solid line. So a dashed line means it does not include values on the line. So this is the line y equals x plus 4. And we'll still shade in this area above the line. So solutions to y is greater than x plus 4 are all found in the green area, not in the line y equals x plus 4, and not on the line itself. Okay, so this line here is what we would call a boundary line. And okay, and so the boundary line sometimes will be a solid line and sometimes it will be a dashed line. So whenever you've got greater than or less than, then the boundary line that you draw is going to be dashed. And anytime you're trying to graph an inequality that has equals in it, the boundary line is going to be a solid line. So that's why in this first example, the boundary line was a solid line because we had greater than or equals to, whereas in this second example, the boundary line was a dashed line because this was only greater than. It did not have equal to in it. All right, let's stop there.